Start.
Okay, this is very important for your examination. This is about the simple pendulum. This is the one of application of a simple harmonic motion. You can see here, this one is the bob of pendulum, which is in a to and fro motion in ACB arc. You know this is the equilibrium position. When it is distorted, it is reaching sometime at this point B and sometime at this point A. A and B are extreme points, and Y is here. You know the Y is displacement, and here is this is Y. You can see when the bob displaces from C to B, it has displacement Y, and L is the one of the inextensible string or the thread of a length L. You know the at which you can see the bob which is attached with this string, and this string is in the where at a rigid support, which is at this rigid support you can see here. And here what have I written is about everything what you can see here in a figure. Here simple pendulum consists small mass bob of a pendulum. Simple pendulum le small mass bob of pendulum consists गर्छ suspended on a light inextensible string of a negligible weight. यो चाहिँ धागोको negligible weight मा चाहिँ यो bob of pendulum ले झुन्ड्याएको छ. That can rotate or oscillate, यताउता हल्लिन जान्छ about the mean position. भनेपछि त्यसलाई simple pendulum भन्छ. Simple pendulum भनेको small mass जो bob जोलाई चाहिँ rigid support बाट चाहिँ inextensible नतन्किने धागोले चाहिँ झुन्ड्याएको हुन्छ, धागोको लोअर एन्डमा झुन्ड्याएको हुन्छ, जो चाहिँ अक्सिलेट गर्न सक्छ मेन पोजिसनमा, भनेपछि त्यसलाई सिम्पल पेन्डुलम भन्छ भनेर यहाँ चाहिँ मैले लेखेको छ. अब त्यसपछि लेटेस्ट कन्सिडर मानौ द नेग्लिजिबल द इनएक्सटेन्सिबल नतन्किने जुन चाहिँ थ्रेड धागो अथवा स्ट्रिङ अफ अ लेन्थ जसको एल छ, एल लेन्थ इज सस्पेन्डेड अन द रिजिड सपोर्ट ओ. यसलाई रिजिड सपोर्ट ओ बाट चाहिँ सस्पेन्डेड गरेको छ फ्रम द रिजिड सपोर्ट suspended on from the rigid support. अब यसलाई झुन्ड्याएको छ भनेको छ. बम अफ पेन्डुलम हैज अ मास m. बम अफ पेन्डुलम को यो चाहिँ यसको मास m छ, इज एट द लोअर एन्ड अफ स्ट्रिङ. यसको मास m यहाँनिर छ, यो चाहिँ भनेपछि यसको मास m छ जो चाहिँ लोअर एन्ड एट द स्ट्रिङ को लोअर एन्डमा झुन्ड्याएको छ. व्हेन द बब इज डिस्टर्टेड, जब यो बबलाई चाहिँ डिस्टर्टेड गर्यो इक्विलिब्रियम पोजिसन, इट स्टार्ट्स ऑक्सिलेटिङ. You oscillating on the arc ACB arc ma your bob of pendulum sometime goes here, sometime goes here. That means when sometime goes here, sometime comes here, and that means it is oscillating. And of this about the mean position ko about mane oscillate bhayerahuncha. Two extreme points A and B, you can see A and B are the two extreme points A and B, which makes an angle theta with the vertically downward acted weight. Vertically downward acted weight सँग सपोज योले चाहिँ थीटा एंगल बनाउँछ भनेपछि यो र यो थीटा एंगल भयो भनेपछि यो भर्टिकली एक्टेड डाउनवर्ड वेट सँग योले चाहिँ के बनाउँछ, थीटा एंगल बनाउँछ भनेर लेखेको छ. दिस वेट रिजर्व्स, यो वेटलाई अब रिजर्भ गर्न सकिन्छ भेक्टर ल अफ रिजोल्युसन अफ भेक्टरबाट. mg लाई के mg cos थीटा जस्तो ए भेक्टरलाई a cos थीटा a sin थीटा जस्तै हामीले टुक्राए जस्तै यो पनि mg लाई पनि mg cos थीटा mg sin थीटा मा रिजर्भ गर्न सकिन्छ. अनि त्यही कुरा लेखेको. दिस वेट रिजर्व्स इन्टु द two component mg cos theta and mg sin theta as shown in a figure. What you can see in a figure, I have written it in this expression in this the paragraph you can see here, right? Now here mg cos theta cancel each other in a string. It is in this direction, this mg cos theta is in this direction, which are in opposite, so cancel each other. There is, while the restoring force mg sin theta, you can see mg sin theta is taking this object from here to at this point or at this point, again from here to here, which force is playing role, mg sin theta. Only here is mg sin theta working, so that is working. You can see here, which gives the bob of pendulum in a to and fro motion, and x toward the mean position. This mg sin theta x toward the mean position and keeps this bob of pendulum in to and fro motion. यताउताको मोसनमा यही mg sin theta ले मात्र उ गरेको छ. अब त्यसपछि देन द रिस्टोरिङ फोर्स, योले रिस्टोरिङ भनेको यो फोर्सले आफ्नो ठाउँमा लैजाने अझ यहाँ ल्याउने, यहाँबाट आउँछ ब्याक ल्याउने यहाँ ल्याउने भनेपछि रिस्टोरिङ फोर्स भनेको चाहिँ mg माइनस mg हियर f इक्वल टु माइनस mg sin थीटा। अब यहाँ चाहिँ माइनस साइन देख्नुहुन्छ, यो चाहिँ जहिले पनि कि कतातिर एक्टिभ भइरहेछ, रिस्टोरिङ फोर्स इक्विलिब्रियम पोजिसन अथवा मिन पोजिसनतिर, त्यही भएर माइनस साइन तपाईँ देख्न सक्नुहुन्छ। यो इक्वेसन यसलाई 2 सपोज गरे, अब A1 सपोज गरे। इफ A बी द एक्सेलरेसन प्रोड्युस्ड बब अफ द पेन्डुलम, बब अफ पेन्डुलममा A एक्सेलरेसन प्रोड्युस गर्ने, देन F इक्वल टु MA बल हुन्छ। यो त पहिले पनि पढेको यो फोर्सको फर्मुला। यो दुईटै फर्मुलालाई हामीले चाहिँ कम्पेयर गर्यो भने F को ठाउँमा MA लेख्यो, mg sin थीटा यहाँ छँदैछ, अनि यहाँ तपाईको mm क्यान्सल हुन्छ, A इक्वल टु माइनस g sin थीटा। सपोज एंगल इज भेरी स्मल, at that time we write sin theta nearly equal to the theta, and then A equal to here, A equal to as it is A minus G equal to G, and the sin theta is equal to theta, because we consider here, we suppose sin theta is nearly equal to the theta. In the place of a sin theta I have written a theta, because theta is, that means sin theta is very small. You know this theta has also value, and which is, we know from the formula arc by radius, theta equal to arc by radius y by l. You can see this is the displacement, which is arc, l is, you know, the length, so that this arc by radius, that means y by l is the formula of what, theta, which we had already studied in lower classes. And when we substitute this y by l value of theta in this equation, you can see, you can get here theta in the place of theta y by l, g is as it is, a is as it is. And from the acceleration of the body in the SHM, you know, if any body is in a SHM simple harmonic motion, it has expression a equal to minus omega square y, which we consider equation 4th. This is equation 3rd. And when we compare, these two are the same equation, you know, this is from the body in the simple harmonic motion, this we have calculated from this figure. And when we compare these two equations, y equal to y and a equal to a, and so that you can write omega square equal to g by l. So I have written omega square equal to g by l, because in the place of omega square, g by l in this equation, we compare the minus sign, cancel each other, and the g by l, we have omega square equal to g by l. When square is removed, then here would be g under root sign, inside the under root g by l, and we know the formula of omega is what, 2 pi by t. T is time period, and here is g by l, and here we are going to exchange them. We are going to take t in the numerator. So when we reverse it, at that time we can write 2 pi by t. Here opposite of 2 pi by t. When we reverse it, then other side we also reverse here, and g by l. You know that I haven't reversed here yet. When we reverse this equation, we can get t equal to 2 pi under root l by g. This is the required expression for this simple harmonic motion. You know, for the simple pendulum, t equal to 2 pi under root l by g, which is required expression for time period of simple pendulum. You can see here formula. When you are told to find the time period of any simple pendulum, you must use this formula 2 pi under root l by g to calculate time period. In this way, we can calculate time period for simple pendulum when it is in simple harmonic motion. Thank you.